Hello everyone. Today we'll learn about phase velocity and group velocity and few important relations between phase velocity, group velocity and particle velocity. These very important topics we'll learn today. I'm Dr. Siddheshwar Chopra and let's get started. So basically what is phase velocity? As we discussed earlier too, phase velocity is the rate at which the phase of the wave propagates in space. This is the velocity at which the phase of any one frequency component of the wave will propagate. The phase velocity is given in terms of the wave's angular frequency, that is omega, and wave vector k, and is denoted by w or u or vp, which is equal to omega by k. And if you open it up, omega is equal to 2 pi nu and k is 2 pi by lambda, that is the wave number, and uh, this gives us nu lambda. So the phase velocity is nu lambda. According to de Broglie, the material particle in motion has two different velocities. One is the velocity of the particle itself, that is denoted by v, and the other is the velocity of propagation of the wave associated with that particle, denoted as Vp, or it is the phase velocity of the wave. Now let us consider, we are basically trying to find what is the expression for wave velocity, which was omega by k. So it's a very simple derivation I've wanted to discuss here. Consider a wave represented as y is equal to a sine omega t minus kx, where a is the amplitude of the wave, omega is the angular frequency, which is 2 pi nu, and k is the propagation constant or the wave number, 2 pi by lambda. So if we say constant phase uh, in the wave, then we are talking about omega t minus kx to be constant. So that is what is your term sine of omega t minus kx, where omega t minus kx is your phase. So phase is constant, so we keep omega t minus kx equal to constant. We differentiate both the sides with respect to time. So we are left with omega dt by dt minus k dx by dt, which is nothing but omega minus k dx by dt equal to 0, or dx by dt is equal to omega by k, which can be called as phase velocity or the wave velocity. Now, another very important thing we have to understand is that the phase velocity seems to be more than c. So that is what we are trying to see in this very small derivation. De Broglie wavelength is given as lambda equal to h by mv, and we know from the Planck's law E is equal to h nu, and from the mass energy relation we know E is equal to mc square. Therefore h nu is equal to mc square, or nu is equal to mc square by h. Now the phase velocity is nu lambda. Therefore, we substitute for nu and we substitute for lambda from the de Broglie hypothesis. So we have mc square by h into h by mv, which makes it c square by v. So we now know that particle velocity must be less than the velocity of light. So that is something known by now. So v is less than c. So if v is less than c, then the phase velocity or the wave velocity will be greater than c, because c square by v it is. So what does it mean? Hence we can say that the phase velocity of matter waves is greater than the velocity of light, which is an unexpected result. Why this is an unexpected result? Because it seems like the particle is reaching at a later point of time, but its wave, associated wave, has reached much before the particle itself. So this problem was solved by Schrodinger, who postulated that a single wave is not attached to the particle, but the material particle in motion is equivalent to a wave packet or a group of waves. So hereby, after this introduction, we introduce another velocity, which is called the group velocity, which is denoted as Vg or G. Group velocity of a wave is the velocity with which the wave packet propagates through the space. It is defined by the equation Vg is equal to dou omega by dou k, where omega is the wave's angular frequency and k is the wave number. Now we would like to find out few relations between these velocities, because now we have three velocities with us. One is the particle velocity, another one is the phase velocity, and third one is the group velocity. So let us find first the relation between group velocity and the particle velocity v. So we know that omega is 2 pi nu and nu from the formula E is equal to h nu we can find. So we have 2 pi E by h, which is nothing but, again I use E is equal to mc square mass energy relation. So we write 2 pi mc square by h. Now we also know that m is the relativistic mass in this case, because the particles we are dealing with here are moving with very high velocities. These are the quantum particles. So basically we have to use the relativistic formula. We have here 2 pi m naught by root of 1 minus v square by c square, that is m times c square by h. So this is equation number 1. Using the relativistic mass formula, we get this equation. Now I have k is equal to 2 pi by lambda. Again we substitute for lambda using the de Broglie hypothesis. So this is 2 pi mv by h. Again I substitute using the relativistic mass formula. So I have new equation 2, which is 2 pi m naught v by h root of 1 minus v square by c square. Now in order to find group velocity, which is equal to d omega by dk, I can also write it as d omega by dv by dk by dv. So what we will do is we'll find the numerator separately and denominator separately, and from the equations 1 and 2, and then we will get the Vg by dividing these new terms. So I need to find what is d omega by dv. So what we do is we take equation number 1 and differentiate it with respect to the velocity. So I get this long equation after differentiation. Similarly, I have equation 2, and which I differentiate with respect to v. I get dk by dv to be equal to 2 pi m naught by h into 1 by 1 minus v square by c square to the power 3 by 2. That is equation number 4. We just divide these two equations, equations 3 and 4, in order to get the group velocity. So we get all the terms get cancelled out, only v is left in the numerator. So we have the group velocity to be equal to particle velocity. So that is one relation we have found just now. We would go for next relation, which is very important to us, which is the relation between group velocity and phase velocity. So we know that phase velocity is omega by k, which implies omega is equal to vp, which is the phase velocity, times k. Now group velocity is d omega by dk. We substitute for omega from equation number 1, we get d vpk by dk, and which I differentiate now with respect to k. We have this d by dk of vpk. So I open it up, I get vp plus k dvp by dk, which I can rearrange to write vp plus k by dk times dvp. This is equation number 2. So what we will do is we will try to find out what is k by dk and substitute back into the equation to get the relation between group velocity and phase velocity. So I have k is equal to 2 pi by lambda. So I differentiate it. I get with respect to lambda, I differentiate. So I get dk is equal to minus 2 pi by lambda square d lambda, which again in terms of k will be minus k by lambda d lambda, because k is equal to 2 pi by lambda, which I rearrange and I get k by dk is equal to minus lambda by d lambda. Substituting for this k by dk in equation number 2, I get my relation between group velocity and phase velocity to be Vg is equal to Vp minus lambda dVp by d lambda. Now it's a very important and interesting relation, which tells me that if a medium is non-dispersive in nature, then the second term, which is dVp by d lambda, is 0 for a non-dispersive medium. Hence Vg is equal to Vp. That means wave packet seems to be moving with exact same velocity as of a single wave. because there is no dispersion in the medium. Now, whereas in a dispersive medium, this term will not be equal to 0. That means Vg is less than Vp. That means wave packet is seemingly moving slower than the phase velocity. So that is all for this lecture. Thank you, everyone.